today's meeting. Gadi and I obviously were connected by mathematics, so we did slightly different mathematics, but we're also connected by the fact that we both have a deep connection to Kibbutz Yagur. Which I think my wife was born on Kibbutz Yagur, and I spent much time there at the swimming pool, being very useful to have a member of the kibbutz because they don't let anybody else near that swimming pool. It's a very beautiful swimming pool. And I suspect, I don't know whether, my wife still has a grandmother who lives in Yagur, who's 104. Wow. Yeah, exactly. Wow. Yeah, amazing. And I suspect maybe Gadi was even taught by her because she was a primary school teacher in Yagur. So I've learned most of my Hebrew from Kika because she treats me like a 5-year-old when I'm in Yagur. So maybe we had the same Hebrew teacher. But I've been asked to give a general talk for the general audience. And I know there are lots of mathematicians here as well. But there are members of the family. And it's always quite a challenging task to kind of give a talk which talks to mathematicians and to the general public. So I thought I would talk about a subject which is very close to my own heart and many mathematicians' hearts, which is the subject of symmetry. So I'm going to start actually with a gunshot. On the 30th of May, 1832, a gunshot was heard ringing out across the 13th arrondissement in Paris. And a merchant who was going to market that morning ran towards where the gunshot was heard from. And he found a young man on the ground, writhing in agony, clearly shot by a dueling wound. And the merchant took this young man to the local hospital, the Cochin Hospital, where he died the next day in the arms of his brother. And his the name of this guy was Évariste Galois. Galois, yes, so he died in the arms of his brother and said to his brother, "Don't cry for me, Alfred, I need all the courage I can muster to die at the age of 20. And now this guy was a very well-known revolutionary in Paris at the time. He caused quite a lot of trouble already. But of course the reason, actually, it isn't very clear what the duel was about that morning. So there are lots of different theories about why he got killed in this duel. One was that it was the establishment trying to get rid of this troublesome revolutionary who was kind of winding things up. Others say it was actually a duel over love, that a friend of his and he actually shared a love for the same woman and they were going to decide who got the woman over the duel. There's even another theory that I read by a biographer in Italy, that in fact he staged his own death, that he wanted to try and spark a new revolution in Paris, and he thought his death would be a good reason to sort of to spark this revolution. So it's still unclear really why he had this duel. But of course it isn't revolutionary politics is the reason why this young man is famous. Because this young man, already whilst he was still at school, amazingly, at the age of 18, had already solved one of the great mathematical problems on the books at the time. And he'd written to the academicians in Paris trying to explain his great breakthrough on this problem. But he couldn't get any of the academicians to take him seriously at all. I mean, how many of you get letters from kind of people from the general public? I get loads. I've got a box full of these things. And but the academicians, you know, but partly the reason he probably didn't get very far was because this is the way he wrote most of his mathematics. So they couldn't really make head nor tail of what he was talking about. So actually the night before that duel, Galois realized that this is probably going to be his last chance to actually explain what he'd done, his great breakthrough. So he spent the whole night writing away, trying to expand on his ideas, explain what he was doing, and the sun rose on the next day, he went out to meet his destiny. Maybe the fact that he'd stayed up doing maths all night was the reason he was such a bad shot that morning, so probably not good planning. But he left documents on his table, and many historians regard those as some of the most important mathematical documents in the history of our subject, because inside those documents were really the beginning of a new language to be able to understand perhaps one of the most fundamental concepts, not just in mathematics, but in science as well, namely the subject of symmetry. This is a new language to try and articulate what symmetry is, and it's called group theory now. We teach all our undergraduates this subject, and it's a subject which I use as a practicing mathematician every day as a research mathematician. But many mathematicians, and Gadi certainly wrote many papers which had connections to group theory, using group theoretic ideas as well. So it's an incredibly important breakthrough that this mathematician made. It's interesting. So I actually wrote a book a few years ago which has been translated into Hebrew it's published, I think, by Books in the Attic. But Galois was my kind of hero of this book, because, I mean, he's such a wonderful character in our subject, this young revolutionary, very romantic figure. And so he's at the heart of this book, which is really a story of humans' attempts to understand the world of symmetry. In England it's called Finding Moonshine. I think in Hebrew it is called Symmetria. But I tried to do something slightly different with this book, because I think that many mathematicians here in the room will have had this kind of experience that their friends and family who aren't mathematicians don't really get what we do. You know, what is it we're doing in our offices up here every day? I mean, I think people understand what a chemist does, mixes chemicals together and they kind of explode, and biologist is classifying butterflies or something. No, sorry, that's right. And physicists are smashing atoms together. What is a mathematician doing? I use this book as well to try and give people a little bit of a backstage pass to what a mathematician is doing all day. How do we do our mathematics? What are we doing? So I decided as well, as a story of symmetry in this book, as well to write a diary. So I kept a diary for a year of what I did as a practicing mathematician. So the book is divided up into 12 months and weaved through the more historical story of symmetry. So I decided I should start my diary on a significant day. So it's a very significant day for any mathematician. It's their 40th birthday. Yeah, see, all mathematicians know that they, not because of some numerological significance of the number 40, but because there's this dreadful myth that we've done our best work by the age of 40. And we even have our Fields Medal, our Nobel Prize, is only awarded to people under the age of 40, which kind of fuels the myth. And here was Galois, at the age of 20, he'd already revolutionized the work that he was doing. So slightly this book was trying to prove that even when I'm 40, I can still keep on doing maths and be interested in mathematics. So interestingly, my 40th birthday was actually spent around here. So I was actually on the beach in Sinai. When I'm born in August, I'm very youngest in my school year, I was. So my wife and I were out in, I think we were in Daha, but no, this probably is Nueva, actually. So the book starts with my 40th birthday. Oh, that's good, yeah. More like a cinema. Now we can see Sinai. So. In fact, we spent our honeymoon in Sinai as well, so it's a very place that's very close to our hearts. But actually, when I don't know about the mathematicians here, but when I was a kid, I didn't even know what a mathematician was. I certainly wasn't interested in becoming a mathematician. In fact, unlike Galois, I think, who was driven by mathematics from a very early age, my dream, actually, when I was grown up, was actually to become a spy. So this was partly fueled by my mother. my mother had been in the Foreign Office, and when she had children, she had to. She was moved. She actually retired from the Foreign Office, but she persuaded me and my sister that they let her keep the black gun that every member of the Foreign Office gets given, and that it was hidden somewhere in our house. So me and my sister would try and look for this gun, but they obviously taught her the art of concealment very well as well. But I became convinced that my mum had been a spy, that she was somehow James Bond or Jemima Bond or something. So I decided I should join the Foreign Office like my mum. And Foreign Office, so I realised Foreign Office means learning languages. So when I went up to my secondary school, I started taking all the languages that I could find. So I started learning, of course we learned French because that's the nearest country to us in the UK. Well, not much now as we drift further and further from Europe, but that's another story. We learned German, we actually had some Latin still. On the BBC there was a Russian course. And I thought, that's great for a spy. So I got my French teacher to help get, this shows how old I am, that actually, the problem with Russians. Well, actually, no, that's coming round again, so we should be all right there. So I got my French teacher to teach me, help me teach the Russian course. But I began to get more and more frustrated with these languages. You had to learn these strange spellings of everything. There were all these irregular verbs. I was, hankering after some logic to this whole thing. And the Russian course was a complete disaster. I mean, I couldn't get past the word for hello, which is pretty basic. But well, there's probably some Russian speakers here. What's the word for hello?
Don't read it.
Oh, there's another word.
Good morning.
Yeah, that's it. You see, it has say it again. Oh, where did it come from? Yeah, thank you. Yeah, see, it has so many consonants and no vowels at all. And it was the name of the course even, so I couldn't even say the name of the course. So I got very disillusioned with this dream to become a spy, having trouble with all of these languages. I've since added Hebrew to a certain extent. My wife speaks a lot in her sleep, and I was determined to know what it was she was saying. So I did an ulpan here when I was a postdoc. But there's still, Hebrew's got some nice kind of mathematical side to it, little roots and things like that. But I realised this wasn't the subject for me. And then I was about 12 or 13, and my maths teacher at my school, in the middle of the class, suddenly went, "Sautoy, I want to see you after the class." Gosh, I'm in trouble. So at the end of the class, I went up to see the teacher, and he said, "Come with me." Oh, gosh. And he took me around the back of the maths block. And I thought, oh, I'm really in trouble now. What's going to happen? But then he got out his cigar. He used to smoke a cigar around the back of the maths block because the teachers wouldn't let him smoke in the common room. And he said to me, "Marcus, I think you should find out what maths is really about, because it isn't what we're doing in the classroom. With all this kind of long division, sines, cosines, it's something much more exciting." And I owe this teacher so much, and I think probably all of us who became mathematicians have somebody, something that inspired us. For me, it was this mathematician who just opened up this magic secret garden of mathematics. And he recommended a few books to me that he thought would help me to just bring this subject to life. And I grew up near Oxford, so I'm a professor in Oxford now, but we grew up in the countryside near Oxford. And we went up to Oxford because my dad had been told about this bookshop, which will have every book you want. I don't know, how many people have visited Oxford? So you probably know Blackwell's bookshop. So Blackwell's bookshop is this kind of like, well, when I arrived, actually, if you notice, it's a little tiny little shop front. You think, well, how is that going to have all the exciting books? But are there any Doctor Who fans here? We have this science fiction thing. There's one Doctor Who. I grew up on this science fiction TV series where this guy travels around the universe in basically like a telephone box. It's a police box. But it's a very small thing, but when you go inside, it's enormous on the inside. So this bookshop was a bit like that. You open the door, go in, and suddenly this completely enormous bookshop. And the maths books were down in the basement in this kind of cavern. It's almost like Aladdin's cave of science books. So we went down there, and my dad had this list of books and we got the books, he got the books, and I wandered around sort of pulling books off the shelves, and I couldn't understand a word. It seemed to be all in code, but I could see these undergraduates leaning up against the bookshelves, reading these things as if they were wonderful sort of detective stories or novels, and I realised there must be some great stories in here to learn. And so I took these books back, determined to kind of decode this secret language. And it's interesting that one of the books that my teacher recommended to me was this book here. It's not a very well-known book. It's called The Language of Mathematics, and I actually brought it along. This is the book. This is the very book we bought too many years ago. It's almost in old money, actually, in England, but it costs £1.25, and I defy you to find a book in England costing that now. But this book really captured my imagination, partly because of the name, because here I'd been trying to learn languages, and I couldn't get past all of these strange irregular verbs and things. And then here I was being told that mathematics is a language, and I'd never thought of maths as a language. So I began to read this, and I realised what an amazing language it is. I mean, it's a language which describes our universe around us. It's a language with no irregular verbs. Everything makes logical sense. But that's not to say it's not a language which has strange twists and turns, and that's what makes it exciting. Not everything is completely predictable in this language, but everything made logical sense, and so I began to fall in love with this language and realised this is the one that I wanted to learn. And there was one language that this book talked about, which is the one I realised that's the place I want to be, which is this language that Galois developed, the language of group theory and symmetry. And that was the one that sort of started to obsess me at school and the rest of my life, really. So, and I understood actually that symmetry, in a way, is a language. Symmetry is a language that nature uses to denote things with significance. So if you go into the garden, for example, and you see a bumblebee flying around, a bumblebee has very bad vision. It finds it difficult to judge distances, has strange colour perception, but what it can pick out are shapes with symmetry. It knows to be attracted to a shape with symmetry because that's likely to be sustenance for it. And the flower itself knows it needs the bee, so it knows that it needs to find some way to attract it. So it seems like there's almost a dialogue going on here between the bee and the flower, and the symmetry is the language that it's using. And there's been research to show that the more symmetrical a flower, the sweeter the nectar inside the flower. And actually humans too, we use symmetry to communicate with each other. If I show you these two photos and then I make them artificially symmetrical. So I then ask you, which ones do you find more beautiful? The two faces on the top or the two faces on the bottom? And most people will say it's the ones on the bottom that they find more beautiful. The more symmetrical, the more we associate that, interestingly, with beauty. Why is that? Well, actually, this is communicating important information. This is communicating that it's hard to make symmetry. Symmetry gets disrupted very quickly. If you have a symmetrical face, it's probably an indication that you've got good DNA, had a good upbringing, you're probably going to make a good mate to have children with. So that symmetry is telling you important information. So that seems to be perhaps why we associate symmetry and beauty. And I love this quote of Galileo's, which some of you probably know already, which I think sums up the power of mathematics and particular symmetry as a language that kind of reads the world. Galileo wrote, "The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometric figures, without which means it is humanly impossible to comprehend a single word." So the journey of this book that I wrote was to try and understand, how do we understand this idea and concept of symmetry? When did humans first start to explore concepts of symmetry? So actually in the second chapter, chapter September, I set off trying to find out what were the first symmetrical objects that humans kind of created. Actually, an important character in the book, as well as Galwa, is my son Tomer. Tomer was 9 years old at the time that I wrote this book. And I used him as a kind of partner in this journey, in a way because he had a very innocent set of eyes. I had too sophisticated. I'd learnt this language of symmetry, and I was interested how he, as an innocent set of eyes, would view the world of symmetry. So we went actually down to the British Museum together, and we explored the museum trying to find examples of early symmetry. And we found this wonderful game. It's called the Game of Ord. So you can see the board there. I think I've got, yeah, here's a picture of the board. This dates back to 2600 BC from the city of Ord. Already the board has got beautiful symmetry inlaid in it. So this game is actually an early forerunner of the game of backgammon. But it's the dice that are the interesting objects in this case, because clearly, if you want a dice, you want it to be fair, such that it lands on any side equally often. So symmetry is going to be an important ingredient for making good dice for a game. So the first dice, not the cubes that we play in today's backgammon, but these little tetrahedral dice. And actually the first dice, of course, I mean, there's a place south of Tel Aviv that you can go and do archaeological dig, and you can take your children there because they've got so many pots and things. There's layers and layers of society. And we kept on digging up bones. We were saying, is this bones to eat with? And they said, no, these are bones that were early dice because they used knuckle bones of sheep. But they weren't symmetrical, so they gradually started to carve them. But these knuckle bones of sheep actually have naturally 4 faces. And so you say, well, what's a shape with 4 faces which is symmetrical, so it's really a fair dice, and you get the tetrahedron. So, of course, unlike a cube, there's a point sticking up. So the way you would read this, actually there should be 2 colours on here. So 2 corners were coloured black, 2 white, and you would throw a load of tetrahedron, and you would count the number of points sticking up, and that would be your turn in the game of Go. In the game of Or rather, the game of Go is another. So these little tetrahedrons seem to be the first symmetrical objects that we could find. But actually in my local museum in Oxford, the Ashmolean Museum, there are another set of symmetrical objects carved about the same time, which are these Neolithic stones, which were discovered in Scotland. And there are about several hundred of these in both the Ashmolean and the British Museum. And you can see here the artist is really beginning to explore different ways that you can put patches on a ball and arrange them symmetrically. It's a little bit like a football or something, these patches. And so you can see the tetrahedron, the cube, but also some other ones here as well. So this dates back 2500 BC. And it's not sure what these stones were for. They don't seem to be part of the game. They may have been used for divination. Sometimes they had some carvings on the little patches, but it's still a bit of a mystery. Or was it just, first mathematicians exploring what's possible in the world of symmetry? We really have to wait till the ancient Greeks for a first kind of mathematical analysis of symmetry, and Euclid's Elements culminates with a proof that there are actually only 5 dice that are possible. So if you have a 3-dimensional shape where all the faces are symmetrical, arranged in a symmetrical manner, then there are only 5 different possibilities. I grew up playing Dungeons and Dragons. I don't know whether there are Dungeons and Dragons. Yes, good there. Yeah, it's always the same people. Who knows Doctor Who? You see, exactly. So Dungeons and Dragons use all the different dice possible. So I remember playing with a 20-sided dice. But Plato writes about these solids in his dialogue Timaeus, and he actually associates them with the building blocks of nature. He believed symmetry was so fundamental that that was the shape of the natural world at a fundamental level. So the building blocks, the atoms at the time were earth, wind, fire and water. So the tetrahedron, this spiky pyramid, that was the shape of fire for Plato. The earth was a stable cube. Air was an octahedron, which is 8 equilateral triangles put together. You can put 20 equilateral triangles together to make the most spherical of these shapes, and that was the icosahedron. That was the shape of water. But then Plato had one shape left over, which was the dodecahedron, which is this beautiful shape with 12 pentagonal faces. And in fact, I use this shape to keep track of the evolving year as I go through the book, so the shape changes. And there are examples of these dodecahedron with calendars on the side, signs of the zodiac, so this has already been picked up. Plato then associated this shape with the shape of the universe. That at the time the ancient Greeks believed we were in some great big glass ball, and he believed that the shape of this glass ball with the stars painted on would be a dodecahedron. Now, from our modern perspective as scientists, this looks a crazy classification, but actually Plato had already got to something very deep, which is that symmetry really is at the heart of the way the natural world works. Take even the dodecahedron. Now we believe the universe might be finite, but obviously it's not contained in some ball. We're not living in the Truman Show with a kind of film crew filming us from the other side, but we believe it's somehow looped. Now you could loop a cube up by anyone who's played the game of Asteroids knows that you zoop off one side and you come in the other side. Do you remember this computer game, this little spaceship, and which shoots off the top of the screen and reappears at the bottom? Well, there's now some belief that the universe might be a sort of joined up dodecahedron, that one face is actually joined to the other, and that the shape of the universe might indeed be a kind of fused dodecahedron. So it's amazing Plato already had this insight. But if you look at a more fundamental level, then certainly chemistry, any chemistry student needs to learn about symmetry to understand crystals and how molecules are put together. Even biology, actually you don't want to get a symmetrical object in biology because they're not very nice. So most viruses have a symmetrical shape. Why? Because they want to replicate themselves very quickly. They have a very small bit of RNA, DNA at their heart, and they need a very efficient program to be able to recreate themselves. So this is, symmetry is often a very efficient way to reproduce, and it's also a very strong shape. Fundamental physics as well. If you look at the Large Hadron Collider or the particles we've been able to predict, it's symmetry which has actually taken fundamental physics from being a subject which was starting to look a bit like biology, where more and more particles were being found and there didn't seem to be any sense to these particles. But symmetry was the way to bind these particles together into a coherent story and even enable us to make predictions. So amazing, Plato was really on the nose when he understood that these symmetrical shapes would be at the heart of understanding the scientific world. But they're not only important to scientists, and a lot of artists as well, I think, have had an interesting relationship with the world of symmetry. But not always an easy one. I think artists have a kind of slightly ambiguous relationship with the world of symmetry. Here's Thomas Mann in The Magic Mountain talking about symmetry. If you've read this book, you'll remember that towards the end, one of the characters goes out from the hospital and gets caught up in a snowstorm. And he almost gets killed by this snowstorm. And he sees the flakes of snow falling on his arm, and he sees the beautiful symmetrical shape, and then as he looks at this symmetry, he said, "I shuddered at its perfect precision, found it deathly, the very marrow of death." And I think for many artists, it's the kind of controlling nature of symmetry which makes them a little bit uneasy. My wife actually, she was at Bezalel, the Art Academy in Jerusalem when I met her, and I said, I'm a keen fan of Escher. And she went, "Pah, Escher." And I think many artists find the symmetry of Escher, whilst as mathematicians we get excited by it, she found it just too controlling, too predictable about what would happen left. Didn't leave room for kind of exciting things which might go against symmetry. But I think there's one art, actually, as we were sitting listening just before I was introduced, we were actually listening to a piece of Bach, Bach's Goldberg variations. And I think there's obviously a lot of connection between mathematics and music. How many mathematicians here play a musical instrument? Do we have? We could probably get an orchestra together. Certainly there seems to be a close connection. I play the trumpet. Is there a trumpet in here? But what? Sorry.
My son-in-law.
Oh, fantastic. Okay, well, I'll bring my trumpet next time. So, good. But I think that the world of symmetry is very much a tool that, for example, Bach used in the Goldberg variations. I would say the Goldberg variations, this beautiful piano piece, is almost like a song to symmetry. The piece starts with an aria, and then Bach does 30 variations, and then finishes with the same aria. So you almost have a sense of a circle being joined up at the beginning and the end. And actually, if you look at the 16th variation, Bach calls it an overture. Now, an overture is usually the beginning of a piece, but it's sort of halfway around. So he's already saying, oh, I don't know where the beginning or the end of this piece really is. Then every third variation is an example of a canon. So a canon are these things you probably sang at school, where somebody starts singing, and a little bit later, the rest of the class joins in singing the same thing, but with a bit of a delay. And the art of a canon is producing, one tune which can be sung in two different time zones. So every third variation is a canon. But Bach wasn't content simply with just the second voice repeating the first voice. So in every subsequent canon, so in the sixth canon, for example, the second voice takes a step upwards and starts one note higher. And then in the ninth canon, it starts two notes higher. And gradually, the second voice climbs through the canons until something rather magical happens when you hit the eighth canon, because then you hit the octave, and the octave sounds like the note you started with again. So it's almost like he's joined up the circle in the canons as well. So for me, I can really hear a sort of like a circle's worth of circles in this piece, or maybe even a spiral. So there's almost the sound of the torus embedded in this piece. And again, the canons, he makes sure that, so there are different rhythmic variations you can do. So you could divide the bar up into 2 beats, 3 beats, or 4 beats, and each beat could either be quavers, triplets, or semiquavers. And Bach, like a true mathematician, goes through all the different possibilities, making sure that each canon combines all the different ways that you could do this. So a little bit like 2 triangles, like a combination lock, making sure that everything is covered. So there's just so much symmetry in here. Even the variations themselves, very often Bach will use some symmetrical tricks. If the voice goes upwards, then the variation will do a reflection, and it'll be a reflection of the tune downwards, or maybe a translation, or even a rotation. So let's hear a little bit of that symmetry at work in one of the variations. Well, Bach's student, Mitzler, used to say that Bach's music was the process of sounding mathematics, and I certainly think this piece is the process of sounding symmetry. But we probably had to wait till the 20th century for composers to sort of pick up this idea of threading symmetrical ideas through their music. Certainly Schoenberg uses kind of symmetrical ideas in his musical practice, but I particularly like this guy here, Xenakis, Yanis Xenakis. He's a Greek composer, and this piece is known, well, this is actually another score. This is a score of Metastasis, which if you look at the score, it looks like a piece of hyperbolic geometry rather than a score. I actually asked somebody who's played this, how on earth do you play? What on earth are you doing? And you're meant to sort of interpret the shape and try and make that sound on your instrument. So, but he wrote a piece for solo cello called Nomus Alpha, which actually he dedicates to 3 mathematicians, including Galois. And in this piece, he uses a symmetrical object to shape the piece. So I'm going to play you a little bit of this piece, and I want you to try and imagine, it's a 3-dimensional shape, what symmetrical object are you hearing when you hear the following piece? Did any symmetrical shapes appear in the mind? Well, I must say even, yeah, exactly, hands in the air, because even when I'm told that that is a cube, I'm pretty hard pushed to hear the cube hiding inside there. But it's probably actually a little unfair, because you probably need to hear the whole piece, because what Xenakis did was to use the symmetries of the cube in the following way. You probably heard all the different musical ideas that the cello can play there. Pizzicato, glissando, turning the bow upside down and hitting the strings of the wood. And what he did was to put these musical ideas on the corner of a cube. And then in each variation, he would do a symmetry of the cube, and then that would give you the new rule for which order these particular musical ideas would be read in. And then he had another cube which was controlling how long you would spend on each one, and another cube controlling the dynamics. And so the restrictions of the symmetries of the cube are actually embedded in the different ways that these musical elements are used throughout the piece. So by the end, you have experienced the 24 symmetries, rotational symmetries of the cube. Xenakis, as well as being quite obsessed with mathematics and music, was also an architect. He worked with Le Corbusier, for example, who was again obsessed with mathematics, Fibonacci numbers and things. And he worked actually on a pavilion in Brussels, which the plans look very much like this piece from Metastasis. And I think architecture is another place where symmetry plays a very important role. So right back to Egypt, the pyramids in Egypt, symmetrical shapes, massive symmetrical shapes in the sand, almost making you feel there might be another pyramid underneath, making an octahedron. Right through to the modern day. So I went to Paris. If you've been to La Villette, which is the science area in Paris, you'll find this amazing sphere, the kind of metal sphere. This is actually the realization of a dream the revolutionaries in Paris had at Galois' time. They wanted to create a sphere which they felt was the egalitarian shape, no direction favoured over any other. So this was going to be a symbol of the revolution. I think they'll be a bit disappointed to find this is actually an IMAX cinema, not a very revolutionary concept. But even here in Israel, there's amazing, if you go down to Ramot, has anyone seen these amazing dodecahedral? I've been told they're really terrible to buy furniture for, though. You have to have specially bespoke furniture to fit in. But I suppose if I was going to be cast out and I had to spend the rest of my life in one building, being somebody who loves symmetry, I think the building that I would choose. I was going to tell you. This is also. I went in November. I went to a conference. So I'm at a conference actually here in Jerusalem for Alex Lebowski's 60th birthday. But the year I was writing this book, I went to a conference in Japan. I worked with a professor there, Professor Kurokawa. And when he heard that I was writing a book about symmetry, he was determined to take me up to Nikko. Has anyone been to Nikko? Beautiful, yeah. So the lovely Shinto shrines and Buddhist temples there, full of symmetry everywhere. But the interesting thing was after we took this photograph together, we walked up the stairs, and you see this lovely arch behind. And there are these 8 pillars, so you can see 4 in front and 4 behind. And they have this beautiful symmetrical design going up the pillars. 7 of them go one way, and then the 8th is upside down. And I said to Professor Kurokawa, wow, the architect must have been so angry with the builders for putting that pillar up the wrong way around. And he said, no, it was a very deliberate act. That actually the architect wanted the 8th symmetry to be disrupted. And he referred me to this wonderful book of essays called The Essays in Idleness, one of my favourite book of essays, written in the 14th century, where in the essays, the essayist writes, in everything, uniformity is undesirable. Leaving something incomplete makes it interesting and gives one the feeling that there is room for growth. Even when building the imperial palace, they always leave one place unfinished. And so this upside-down pillar was actually that disruption of wanting everything to be totally uniform. And actually, even if you go back to the Goldberg variations, the last variation, the 30th variation, you think you know what's going to happen because there's been so much symmetry and pattern built up, completely disrupts it. It's like the upside-down pillar, so it's called a quadlibet, a musical joke, and it's just a variation on 2 folk tunes of the day. It has nothing to do with the rest of the piece. but almost illustrates how much symmetry there was that you were expecting something completely different. So I think artists like symmetry because they can set up expectations that then they can break. But if I was going to be cast out into one building in the rest of the world, I think actually all of these are wonderful, Ramat, Nico, but I would actually choose the Alhambra in Granada, because the palace in the Alhambra is a real, if Goldberg Variations is the song to symmetry, this is the palace celebrating symmetry. Because as soon as you go inside the palace, there is symmetry absolutely everywhere. October for us in the UK is a time when schools have 1 week holiday, and so this October I actually took my family off to a trip to the Alhambra to try and explore the mathematical symmetry in the Alhambra. My family are thoroughly sick of my kind of nerdy mathematical holidays that I inflict on them, but we went off to the Alhambra to explore the symmetry of the Alhambra. So this is Tomé looking very not very happy about being there. But already when you go in, you can see the first sort of symmetry, which is reflectional symmetry of the water. There is water everywhere, just throwing up a mirror image of the buildings behind. And I remember after we took this photo, a girl ran up and put her hand in the water to try and catch one of the fish, and it completely destroyed this beautiful image of symmetry in the water. And it made you realise how special symmetry is. It's very easy to disrupt it. So the water kind of almost illustrated that. But it's really on the walls in the Alhambra where you see the symmetry really at work. And of course, actually, Escher made 2 trips to the Alhambra. He actually, if you look at his art before he did all of these tilings, it's very three-dimensional, and it's pictures of the Amalfi Coast. But after going to the Alhambra, he started to get obsessed with his own ideas of symmetry on the walls. So I took my son there, and I was interested to show him some of these walls and ask him, well, do you think these walls are symmetrical? The first wall you see when you go into the Alhambra is this one here. And when he looked at it, he said, well, I don't think there's any symmetry at all. You see these weird little pieces here, sort of strange shapes. And I think this is, somebody, when you say symmetry, their first perception is, well, what's the big deal? Symmetry is just left-right reflectional symmetry. And this is the kind of journey we've been on. We understood that symmetry is so much more than just left-right reflectional symmetry. And this is the kind of breakthrough that Galois made, that Galois understood that symmetry isn't static, it isn't deadly, it's full of motion. It's the things that you can do to those tiles, move them, such that when you put them back down again, they look like they did before they moved them. And so symmetry in this wall is all about motion. What can you do to this wall, change it in some way such that it looks like it did before you moved it? And so I tried to describe to Tomer, actually, that symmetry is a bit like an object's kind of magic trick moves. If you take a shape, like a cube, you ask the person to close their eyes, and then you move the cube and you rearrange it, but when you open your eyes, it looks like it was before you moved it. And so Galois realised that somehow the symmetry is all the ways you can move these objects, not just physical, but sometimes mathematical, abstract objects, in such a way that when you put them back down again, they look like they did before you moved them. And this began to give you actually a language that Galois developed to be able to read these walls in the Alhambra. So I think the Alhambra is a great place to take somebody to explore the world of symmetry, because all the questions are there. Did the artist in the Alhambra discover all the different symmetrical possibilities to tile the wall? When are some of those tiles actually expressing the same symmetry? How can you say that? How can you say that these walls have the same symmetry? And it was Galois who realised that you've got to look at the way that these you can move these tiles. So I apologise to the mathematicians here, but I just want to take 2 very simple shapes and just explore the symmetries of those shapes, so you can understand what this means. But we're going to push it a little bit further, because it's not just the symmetries of these shapes, but how they interact with each other that Galois realised was important. It's not just the words, it's somehow the sentences you can make with these words. So let's just run through the symmetry. So what can I do to this object? Well, I can turn it by a 1/6 of a turn, put it back down again, looks like the starfish before I moved it. Or I could move it by a third of a turn. That's another symmetry. So I've got two symmetries, but there's a few more moves. I can do half a turn. So my little yellow dot is just keeping track of what we're doing. 2/3 of a turn, and then there's 5/6 of a turn. So I've got 5 different moves already I can make to this, which pick it up, move it, put it down. So 5 symmetries. But Galois realised actually there was an important 6th symmetry here, which is when you say, what, flipping it over? No, flipping it over won't do because I put a little twist on it, so it's got no reflection or symmetry. The 6th one is just leaving it where it is. It's like 0. The number 0 is a big discovery in numbers, just leaving something where it's doing nothing. So everything has one symmetry, which is just leaving it where it is. This has 6 symmetries. Now let's take the triangle, because this also, interestingly, has a rotation a third of a turn clockwise, a third of a turn anti-clockwise, but we've got 3 reflections. We could reflect through the line through X, or flip it in the line through Y, or flip it in the line through Z. So again, 5 different moves, and then we could just leave it where it is. So 6 moves. So these two objects both have 6 symmetries. So maybe we should say they have the same amount of symmetry, the same symmetry. But no, there's a way to distinguish why these are 2 genuinely different symmetrical objects. And Galois' insight was to realise, just don't regard the things on their own, but how do these symmetries interact with each other? Because if I do one magic trick move followed by another, the combination is a third thing I could have done to it. So there's a kind of grammar at work here. So I think for me this is the magic that Galois, the revolution that Galois instilled, is to somehow make geometry into algebra. And I think many of the key moments in mathematics is when you suddenly find a way to change one thing which is quite hard to get your hands on into something completely different, which gives you a language to talk about. So Galois realised, well, what if I did, say, a 1/6 of a turn followed by the 1/3 of a turn? Well, let's do that. I've named the one, so a 1/6 of a turn is capital B. Let's follow that by a 1/3 of a turn, which is capital C. But the combination, if you combine those, it's just like doing half a turn. So this table here records what happens if you do one rotation followed by another, if the combination is a third symmetry. So this tells you how the symmetries interact. And interestingly, it doesn't matter what order I did that. What if I did the 1/3 of a turn first? I do the C followed by the 1/6 of a turn. Well, it still ends up being the same place. It's a half a turn. So there's actually a symmetry here. If you look at this line here, everything that happens in the top half also happens in the bottom half. So it doesn't matter what order you do the symmetries here. But if you take the triangle, it does. Let's do a 1/3 of a turn anti-clockwise followed by a reflection in X. The combined effect is as if I'd reflected in Z. But if I do it in the other order, let's reflect in X and then do a 1/3 of a turn anti-clockwise, which I called U, then actually the result is different. The combination is a reflection in a line through Y. So now the way the symmetries interact, it matters what order you do them in. So this new way of looking at symmetry, combining them, which is what group theory at its heart is about, starts to allow you to see why 2 objects might have different symmetries. But it also allowed you to say, well, suppose I've now got another object with 6 symmetries. Galois kind of came up with some rules for the way these tables can be filled out. And he showed that, well, if you've got another object with 6 symmetries, either those symmetries have to work in the same way as the triangle or the starfish. But actually there are only 2 objects which have different symmetries with 6 symmetries. And any other object will have symmetries which work in the way this table works or the way the other table works. So this language gives you a way to read the walls in the Alhambra. So, for example, here are 2 very different walls. This is one of my favourite ones with this kind of shimmering triangle. And then this very interesting one here with sort of Magen David with these kind of Z shapes around it. So these actually have the same underlying symmetries. They look geometrically very different. But if you use this language for how the symmetries interact, actually they're doing exactly the same thing. So what are the symmetries? They're the magic trick moves. So there's a place where I can turn the tiles by a 1/6 of a turn, where they meet here. So we're ignoring the colours. So there's a 1/6 of a turn, but I can take the centre of these little shimmering triangles, do a 1/3 of a turn there, and then there's another interesting symmetry which is halfway along. So if you actually rotate by half a turn, then the bottom, this triangle flips around to here, and this one up to here. So there are 3 different places with these different symmetries. But if we now look at this other wall with the Magen David, take the centre of the Magen David, you rotate that by 1/6 of a turn, all the tiles match up. Then there's a place where the Z pieces meet, that's 1/3 of a turn that you need to match all of those up. And then one which is quite hard to find, which is halfway between the 6-pointed stars. If you do that half a turn, the 2 6-pointed stars swap over, and you get the same symmetries. So this language enables us to say, well, these walls have the same symmetry, even though they look very different. So that one's symmetry is called 632. Actually, if you're a chemist, you call it something else, but they rather messed up the nomenclature of this system. So, but here's 3 different symmetries. Again, the entrance to the Alhambra, the wall, and the floor, they all have the same symmetry called 442, which has nothing to do with football, but with the fact that there's a 1/4 of a turn in 2 of the places and a half turn. But again, these, although they look very different, the language of Galois enables us to say that actually these are the same symmetries. So we've got 2 different symmetries. By the end of the 19th century, Galois, of course, had already died by then in the duel, mathematicians had used this language to understand there are actually only 17 different symmetries that you can do on the walls in the Alhambra. That when Escher tried to create an 18th design with all those angels and devils or shells, the mathematicians already could prove that nothing he could do could squeeze a new way of getting symmetry on the wall. So actually in this chapter in October, I was interested to see, did the artists in the Alhambra who were doing this in the 14th century, 15th century, had they discovered all 17? They almost did. I managed to find examples of almost all 17. Sometimes you have to preserve colour in here, but this one was the one that really foxed me. So if you coloured these blue tiles black, then actually this had the 17th symmetry. So I was very tempted to take one of my black markers, but I thought, oh, I'll get into trouble, so I just did it in my mind. But it's amazing that these artists actually, just through exploring through what's possible, had actually come up with a 17, but it took the mathematics of Galois' language of symmetry to show that actually there wasn't anything more than these 17. And actually Galois began us on a journey which took about 150 years, where he understood that symmetry actually has kind of atomic symmetries. The most important thing in the chemistry, the periodic table, the atoms from which all molecules are built. Galois understood that symmetry had its own kind of atomic symmetries. All symmetries could be broken down into symmetries of kind of some indivisible symmetrical objects. So, for example, take a 15-sided coin. Well, the symmetries of the 15-sided coin can be made out of symmetries of a triangle and a pentagon inside. But he realized it wasn't just these simple prime-sided shapes. For example, if you take the dodecahedron that Plato had, that has 60 symmetries. 60 is very divisible, but Galois' work had already enabled us to understand that that was the rotations of a dodecahedron are one of the atoms in the periodic table of symmetry. And so it started this journey, which took 150 years to complete our periodic table. And in 1985, we finally recorded this kind of periodic table. It's called the Atlas of Finite Simple Groups. It has a list of all the finite symmetrical objects, the indivisible ones from which all others can be built. I've actually finished my undergraduate degree in Oxford around this time, and I wanted to carry on my research into symmetry. And I realised that Cambridge, actually, in the UK, was one of the centres of where this classification of these building blocks was going on. So I went up to Cambridge to talk to one of the authors of this amazing thing, which had just been published. And I went to see John Conway, who I'm sure has come and talked here in the University of Haifa. And he was one of the authors of this amazing book. I didn't want to bring this book along, but it's almost as big as this slide, actually. It's here in the library. You should go and have a look at it. It's absolutely fascinating. It's got no pictures in at all. It's just full of this language to describe this thing. But Conway was very proud of this, and he brought this book into the common room in Cambridge, and he slammed it down on the table, and then he said, "What's your name?" And I said, Marcus de Sautoy. And he says, well, I'm afraid you're going to have to drop the do if you want to join our group. I said, well, what's that about? Has he got something against French aristocracy or something? He said, no. All the authors who contributed to the final classification, they all had 6 letters in their name. And Sautoy was fine, but do was just going to mess it up. So, so he said, I'll drop the do. He said, but you got initials? He said, yes, my initials are MPF. So I said, no, you've got to drop one of those, because all the authors who'd been authored this book, they only had 2 initials. So I thought, okay, MP Sautoy. He said, no, we're really obsessed with symmetry here, so there's another condition. So, okay, what's that? So he said, well, John Conway was the first who had the idea. This is actually the culmination of hundreds of mathematicians' work across centuries. So these 5 authors are the ones who just recorded this in. They did a lot of great work. But anyway, John Conway had the idea of putting it inside this thing, an atlas to help you navigate symmetry. His student, Rob Curtis, joined the group and helped Conway. And then there was this rather weird guy who kept on hanging around the department outside their office called Simon Norton. And eventually they realised actually he has an amazing ability to navigate these symmetries. So they asked him to join the group as well. Parker was a real wizard at the computer and was able to do quite a lot of the computing necessary. And finally Wilson joined the group, the last. If you notice, they all joined in alphabetical order. Amazing. So he said, well, you're going to have to change your name from Sautoy to Zotoy if you're going to be the next one on this list. And by that time I thought, well, that's too much. I'm going back to Oxford. And actually I started my doctorate and I began to be a bit worried. You know, maybe symmetry was finished. Maybe actually we knew everything about symmetry now because we got the periodic table, the building blocks of symmetry. But what I realised is, of course, you know, anyone who's a mathematician here knows that as soon as you answer one problem, 2 more appear. It's like a hydra. It's this mythical beast that just seems to grow every time. So, you know, we now have the atlas of finite groups, but we don't know how to put them together. We don't know the molecules, the symmetries you can build from those. And so actually my research since for my doctorate and since then I came here to work with Alex Slobotsky, has been trying to understand how to put together these symmetrical objects to make new symmetrical objects. So, and that's actually, I've been working on a conjecture which has been open for 50 years. At the end of the book, I come, end of my 40th year, and I've been working on this conjecture for about 10 years. I still haven't solved it, 10 years later. But I think that's the point. You know, it's the things that we haven't proved that keep us going, in a way. It's fun to talk about the things we do know, but actually it's all the unknown things which are actually the lifeblood of mathematics, which I think is important to tell our students, that there are lots of things that we don't know. I always like coming back to this quote that my Japanese colleague referred me to, because I think it's a really important drive in everything we do in our lives, not just in mathematics. But uniformity is undesirable. Leaving something incomplete makes it interesting and gives one the feeling there is room for growth. And I think that was the realization I had at the end of that book, that actually you always want there to be something you don't know. It's still something to do. And that's why I think, I turned 50 last year. I hope when I turn 60 that, we'll always be driven to try and understand the things that we don't know, of which there are many. Thank you.
Okay, thank you to Marcus for a very interesting and I think accessible talk. So now everyone is invited. I think that we're maybe they'll bring the food in or out. We'll see. But you're welcome to just circulate and they bring it in here and have something to eat and drink. And at 4:30 we will reassemble here to with the family to talk about Gadi. Now, what we talk here about filming this?
I pressed the button which started some sound. I pressed the red button. I press something and I don't worry, I don't know whether I hit this. Well, yeah, you had that time. I pressed. I pressed the button.